When we map metabolisms on the overall tree of life, we find that many basic groups of metabolisms evolved very early in Earth history. We can take these major groups one at a time. Oxygenic photosynthesis, as used by cyanobacteria, originated more than 2 billion years ago. The first record of cyanobacteria is at 2.72 billion years in stromatolites from the Tumbiana Lakes of Australia. Here we infer that there was oxygenic photosynthesis, and hence cyanobacteria, since other metabolisms were excluded for geochemical reasons from these lake environments. About the same time, we have cyanobacterial biomarkers described by Brox et al. 1999 in rocks that are 2.69 billion years old. Brox's evidence is based on biomarkers in oil, and it was not long before Rasmussen et al. 2008 challenged the record as contamination, since oil from younger rocks could migrate into the older rocks studied by Brox et al. Rasmussen et al. Argued that, in fact, the first appearance of cyanobacteria was at 2.1 billion years, and the first eukaryotes are no older than 1.8 billion years. But analysis later on by Waldbauer et al. 2009 of a South African borehole in 2.6 billion-year-old rocks found biomarkers for cyanobacteria and eukaryotes in confirmation of Brox's earlier claim. This back and forth of discovery, refutation, and new discovery is very common in studies of the early Earth. When it comes to sulfate reduction, Shen et al. 2001 found sulfur isotope evidence for this metabolic system in 3.4 billion-year-old Australian rocks. This is an unusually old date, since there is other evidence that the ocean does not become sulfitic until about 2.3 to 2.5 billion years. It appears that sulfur reduction may have evolved long before sulfate becomes widespread in seawater. A third major group, the methanogens, turn up as distinct lipid biomarkers by 2.7 billion years, and as methane in fluid inclusions in chert by 3.46 billion years. The carbon isotope evidence for methanogenesis in the 3.87 billion-year-old Isua supergroup of Greenland suggests that methanogens might be at least as old as our oldest rock record. Now, there is a really cool, relatively new twist to this story. David and Alm, 2011, used a gene database for the Tree of Life to look at genes for specific metabolic functions in living organisms. Their method is really cool because it does not rely on the chemical or body fossil record at all, but instead asks when the genetic machinery for metabolisms evolved. They find that there was a big burst in gene evolution in the Archean about 3.4 to 3.3 billion years ago. Most of the new genes either make enzymes that attack nucleotides or are involved in redox reactions. So, although we do not have a great fossil record, the genes show that life figured out most ways to make power very early in Earth history. This genetic evidence also suggests that there was much more biological diversity in the early Earth environments that then appear in the fossil record. That's not a surprising conclusion, since things like stromatolites only show us that there were microbes about, but are not very specific about who was making the stromatolites. Now, subsequent to this burst of metabolic evolution, there's a massive loss of gene systems in different clades between 3.1 and 3 billion years ago. Apparently, there was a sorting out period of intense selection that resulted in specialization by particular groups of microbes on specific metabolic systems. Later, in the last 3 billion years, there's been a steady loss of metabolic genes and a transfer of genes between different microbial groups, but relatively little new genetic evolution. Now, bear in mind a couple of caveats regarding this genetic approach. First, David and Alm's data are only for gene systems that are still with us. If there were a lot of unsuccessful experiments with metabolic systems before 3.3 billion years ago, we would never know if those novel genes became completely extinct. Hence, there could have been many more births and losses of genes before 3.5 billion years ago that we have no record of. We really have no way of knowing how much unsuccessful experimentation there might have been in the early Earth. The analysis is also dependent upon a molecular clock estimate for the age of various bacterial and archaeal groups. Now, I've not talked much about molecular clocks yet, except to mention them, but suffice it to say that dates of events are not very well nailed down. For instance, an alternative set of assumptions places this archaeal expansion of genetic diversity at 2.5 billion years ago, right about when diverse evidence points to the appearance of an oxygenated atmosphere. But this younger age would also suggest a still younger appearance of heterotrophy and oxygenic photosynthesis that would both be incompatible with the appearance of an oxygen-rich atmosphere at 2.3 to 2.5 billion years. The bottom line is that it looks like life got started with a bang and figured out most ways of making metabolic power very early in the history of our planet. Since that time, the record is characterized by extinction and a lot of trading around of metabolic systems between different groups of microbes. This trading business includes us, since eukaryotes managed to snag most of our metabolic machinery from early appearing bacteria. We're like corporate raiders, seizing the successful ways of doing things that evolved in a burst of innovation that appeared right at the dawn of time.